Well, then let's move to galaxy formation proper, the earliest galaxies that we can see. And there is no natural division between galaxy formation and galaxy evolution, but we usually think galaxies are really high redshift, first few percent of the age of the galaxies and so on. And they form along with large-scale structures in which they live, but they have extra complications in form of star formation, dissipation, and so on. And massive galaxies have done forming by and large. Occasionally they have a major merger. But some of the dwarf galaxies may be just initiating star formation now. So galaxy formation is happening even now. Not very much of it. All right, so nowadays we are studying this at redshifts greater than about 7, which means the universe was 1/8 of its present size and earlier, or roughly speaking, first billion years of the age of the universe. So this is what we think happens. Early on, there are no galaxies, there are no stars, there is dark matter, there are some non-uniformities in it. Those grow under their own gravity, attract baryons, the gas. They become dark halos, which then are containers inside of which normal stuff comes in, and then at some point star formation ignites. And the ultraviolet radiation from those young stars ionizes the gas. Before then, gas is transparent to radio waves and infrared, but not to ultraviolet radiation because it's easily absorbed by hydrogen. After you ionize the hydrogen, it's transparent to UV light too. And that time is called the reionization era. So this is sort of cartoon version of it. You start with the Big Bang, there is microwave background, and there is what we call dark ages. There is nothing shining light in the universe. Dark halos are slowly assembled, gas into them, star formation ignites, and just removes all the neutral hydrogen, the universe becomes transparent, and then this is what we observe as galaxy evolution from then on. So if you want to observe them, first thing you ask is, where does the energy come from? And there are 4 potential sources of energy for young galaxies. First of all, you're collapsing larger cloud into something smaller, you have to get rid of the binding energy. That turns out to be of the order of 10 to the 59 ergs for a typical galaxy. But the real energies in nuclear burning in stars is an order of magnitude more, so integrated over whatever took however long to the star formation, it could be 10 to the 60th ergs for a typical galaxy. Now, it's probably coincidence that the amount of binding energy that was released in converting interstellar clouds into stars is about the same as it took to assemble the galaxy, about 10 to the 59 ergs. And then if you have active nucleus, quasar, black hole, that can do anything, from nothing all the way to about 10 to the 60, 61 ergs, depending how luminous it gets. So there's plenty of energy. Some of that energy then ionizes the gas, just like star-forming regions like Orion and Nebula, and the gas emits in fluorescent lines, recombination lines, hydrogen, oxygen, what have you. And by far the strongest of those will be Lyman alpha line, the first transition of neutral hydrogen, level 2 to level 1. And so that was seen as the primary tracer way to find star-forming galaxies with high redshifts. Because high redshifts, that means it's been now redshifted into the visible part of the spectrum, and so you can observe it with normal telescopes on the ground, and you expect it to be pretty strong. So there are 2 ways in which that was done. One is you take spectra on the sky, occasionally you run into one of those things, like that one, you just see the emission lines, emission line and nothing else. Another way to look at them is to take pictures in narrowband filter that's centered on that line and compare that with broader image. And so that's how it looks like. So this is field of some quasar, and the top image on the right is just regular broadband red filter. The one underneath is picture taking in a narrowband filter that corresponds exactly to Lyman alpha line. You can see everything else is suppressed, but this one galaxy really stands out. And that turns out to be emitting companion of that quasar at the same redshift. Both of those have been used extensively, mostly this kind of narrowband imaging. This is one of the most distant, if maybe still the most distant confirmed galaxy with a spectrum, so a redshift of 7. And this was done by a Japanese group on the Subaru telescope. And you can see the pictures. There are 2 filters. There's nothing between those bars. And then you take a narrowband image, and boom, there is a galaxy shining in that emission line. Another method which is now even more popular is so-called Lyman break method. And that was first really done effectively by Chuck Steidel here. And it works like this. You have young stars. There is interstellar medium in their host galaxy, some neutral hydrogen. That hydrogen is going to absorb very effectively all the light blue or the Lyman continuum break at 912 angstroms. If you look far enough, there'll be even plenty of Lyman alpha forest lines to take out everything bluer of Lyman alpha line. Now, spectra of star-forming galaxies tend to be kind of flat, and then you're looking for objects that have flat spectrum in red, and then sudden drop in blue, which is due to this absorption by the gas. And the example is shown there. This galaxy looks more or less the same in 3 fields. This blue, visual, infrared, and it's completely gone in the ultraviolet. And so this turns out to be a very efficient way of finding distant galaxies, which is now being pushed to the highest redshifts that people actually can dare do. These are examples of some candidates for galaxies around redshift 8, 9, 10, 11 from Richard Ellis's work. And you can see that, starting from the left, there is nothing, then suddenly something shows up. And that's interpreted as one of those Lyman breaks. And that gives you the approximate redshift. This is not certain. We'll only know after we get real spectra with a 30-meter telescope, but it's not a crazy idea. So this is what we can do today. And so this is the kind of observations that was then averaged to ask the question, what happens with star formation history at the highest redshifts we can probe, deepest images with Hubble. And that's those points to the right. So there is some uncertainty in those models, but the qualitative behavior is more or less what you expect.